Hello, for students, could you help me check whether you can log into Learning Catalytics to see this session? Okay, I just deliver a question there. You take a look whether you can see the question here. So for student online, student attending on team, could you help me check whether you can see, so you log into Learning Catalytics. You log into Learning Catalytics. Check for this session ID, whether you can see the question I deliver there. Hello? Hello? So whether you can see the question here? Come. Okay, good. Okay, good afternoon, ladies and gents. Time for us to start our class. So, from today, this week, we will start to learn wave optics. So we have already finished the geometry optics. So from this week, we will start to learn wave optics. So wave optics contains also 2 chapters. The first chapter is about the interference of light, which I will talk about today. So next week, I'm going to talk about diffraction of light. You know, the chapter 4 is about the diffraction of light. Then all the contents on physics will be finished next week. Okay, will be finished next week. Some students sent me an email about the arrangement of our next week's class. So as I have already discussed with you last week, next Wednesday is actually a public holiday, but it will be quite difficult for us to form another common hub for all of you available, so that we to make up the class, so that we will still conduct the class exactly, you know, at the same time. Okay, exactly at the same time. Next Wednesday, 1:30 p.m. Next week, 1:30 p.m. we will still conduct the class. So that will be chapter 4 on wave optics. Okay. So let me first start recording this session. Oh, recording started. Oh, okay. So we talk about start all class this week. I have left a question, an actual question for you to rehearse. For example, this multiple imaging system. So as I said, for geometry optics, for chapter 1 and 2 on geometry optics, the most, as I said, the most, not one of the most, okay, is the most important concept is this multiple imaging, okay, multiple imaging question. Okay, so whether we have imaging shown by multiple times by a series of lines on the mirror, I have summarized the semester for you to follow, so that you will be able to solve all the multiple imaging questions. I hope every one of you should try to, digest this recurrent semester, because multiple imaging system, as you can see, was tested quite often in the final examination. Tested very often in the final examination. Okay, so if you are still confused about this multiple imaging, go to look at my tutorial last week and try to digest the recurrent semester. Now this, as I said, this question of course will be very difficult. It will be more difficult than what we tested in the past examination papers. But I think it's a good example for you to take a look to rehearse how to apply this recurrent semester. Now let's look at what it is about. So here we have an optical system consists of 10 identical lines. Their focal lengths are all 8 centimeters. Distance between each neighboring length is set to be a constant 36 centimeters. An object, this is the first object distance, okay? An object is located at 12 centimeters to the left of that one. So this guy is 12 centimeters, which is P1. So I want you to locate the final image on a common length object, such as the magnification and position. Okay, so first let me review what the how to use our recurrence method to solve this multiple imaging question. Okay, so as I said, normally we have a 3 step. So in the question, of course, the focal length of all the lengths on mirror will be given. So Fn is a given number. Okay. So as I said, the object distance for the first image step will also be given. So P1 will also be given. So that in order to solve the last image distance, you have to follow my 3-step recurrence method. So we first start with the first image distance. Okay, the first image distance. As I said, for the first image distance, P1 is given. F is also in the question. So that we apply the image equation. In the image equation, only Q1 is unknown, right? Because the first image distance is given. F1 is given. So for example, I take this question as an example. So my P1 is 12. So F1 is 8. Okay. So that P1 F1 is given, we can start with the first image distance, apply the image equation, we can get Q1. Once we get Q1, we always use Q1 to get P2. Okay, this is the most important concept. If you apply my recurrence method, you don't have to justify whether the image or object formed in the intermediate step is virtual or real. Okay, so that will be quite confused. But if you directly follow this one, you don't have to, judge whether this image is or object is virtual or real. You can directly follow the step till the end. Okay, so the idea to use Q1 to get P2 is P2 equal to D12 minus Q1. What is D12? D12 is the distance between length 1 and length 2. Okay, this is 36 centimeters. Okay, length 1 and length 2. This length 1 and length 2 their distance minus Q1, I can get P2. Once you get P2, you redo 1. And then because P2 is now given, as I said, F is always known. Okay, P2 is known, F2 is known. So that we can use the image equation for the second length to get Q2. Once you get Q2, you always use Q2 to get P3. How to do that? We use D23, okay, n update log to 2, so that is D23. The distance between length 2 and length 3 minus Q2, we can get P3. Right, once P3 is known, then inside the equation only Q3, the third image step, only Q3 is unknown. So that we will be able to use the image equation of the image step 3 to get Q3. And then redo 1 and 2 till the last imaging process. Okay, redo this 1 and 2 till the last imaging process. So now let's look at my solution. So as I said, this is what we know. P1 equal to 12, all the F equal to 8, and all the distance between each length, okay, is fixed at 36 centimeters. So that for length 1, we apply the image equation because as I said, P1 is given, F1 is given, we can directly get Q1. Once Q1 is known, so magnification here, of course, minus Q1 divided by P1 is minus 2. Then we get the first image is from here, okay, and then we get P2, use D12, the distance between length 1 and length 2 minus Q1, we get this 12. Okay, this P2 equal to 12 is exactly the same as P1. So that if you apply the image equation for length 2, you can get another Q2 equal to 24 centimeters, so which is also the same as this Q1, 24 centimeters, with a magnification equal to minus 2. Then once Q2 is known, we can use Q2 to calculate P3. This is my Q2, okay? My Q2, once my Q2 is known, I can use D23, the distance between length 2 and length 3 here, minus Q2, I can get P3 equal to 12. Okay, this is another 12, okay? P3 equal to P2 equal to P1 equal to 12. Then if I apply the image equation for length 3, I can get another Q3 equal to 24, another 24 centimeters, which is the same as Q2 and Q1, okay? Which is the same as Q2 and Q1. So that because each length is identical. For the first length, we can say, for the first 3 lengths, we can say in each image step, the object distance are the same, fixed at 12. And the image distance is also the same, fixed at 24. So that we can get, perhaps for the whole image system, the object distance should always be 12, and the image distance should always be 24. Now we check whether is it. For the last image step, okay, so if we assume, for example, Q9 is 24, right, as I said, each length is identical. So that's the object distance Q fixed at 24, okay, so that you get P2, again 12, this agreeing with your assumption that the object distance is 12. Okay, if the object distance is 12, for the last image equation, you can get another Q10 also equal to 24. So that this confirms that our assumption is correct. That for each image step, the object distance is always fixed at 12 centimeters, while the image distance is 24. Okay, so the last image distance is 24, which means my last image from on the right of length 10. From on the right of length 10. Okay, so this should be a real or virtual image. Any idea? This should be a real or virtual image. Very good. Why? Okay, so yes, that's also one way to look at it. Okay, but as I said, whether to judge whether the image is real or virtual, just look at whether my last image distance q is larger than 0 or smaller than 0. Here my q is larger than 0, so that this is a real image. So the total magnification, I multiply all the 10 magnification together, I can get 1024. Okay, 1024. So you can say, although the final image is a real image, but it's 1024. This is an upright image, okay? It's upright. Although each magnification matters, okay? But you know, we invert even times, and then it get an upright real image. But here, what I would like to highlight is, okay, you can say for each image that the magnification is not much, just 2. Okay, just 2. Not a very large magnification. But now if we have 10 imaging process, 10 cascaded runs, each of them provide 2 magnification, then 10 nuts can give us more than 1,000 times of magnification. This is very powerful. Okay? This approach is very powerful. This is what we use, for example, in our microscope or even in your camera system. If you want to change the distance, the focal distance to image a very remote object, we also use this one. We use this cascaded lens to control the focal length, so that we will be able to image, you know, very remote object. We will be able to image a remote object. Okay, so in your camera system, on your cell phone, we use this cascaded lens. So normally we have 6 or 5 lens cascaded together in your single cell phone camera. Okay, some cell phone has even powerful image system. For example, they have more than 10 nans, so that they will even be able to image object at a very remote distance. So if you search on YouTube, some people can use their cell phone to take a photograph of the moon, so that you can even see the mountain or some details of the moon. Is because of this, their cell phone is very powerful. With this cascaded lens, they will be able to enlarge the moon and even see detail of the moon. Okay, because of the cascaded lens can give us very large magnifications, so that we will be able to see details of a very remote object. Okay, which can be very difficult to capture otherwise. Okay, so any question? So no question. Let's start our class today. So if you have already watched the LAMS or attended summary lecture, you will be able to follow. Okay, so wave op is very difficult. It's very difficult, especially about the interference. What's that about? But what I can say for light interference, what we have to understand, okay, what we have to understand is just these 2 points. 2 points on the one table. 2 points on one table. Okay, 3 slides is okay. So what are the 2 points are? So first, you have to understand light is a kind of wave, not a particle. Light is a kind of electromagnetic wave, not a particle. What does that mean? So when we, for example, first, if for particle, when we, for example, throw, for example, a particle like a ping pong ball through the ball or through a slit, once the ping pong ball passes the ball, it will not change direction. It will continue to propagate on its original path. But the wave does not do the same. Light is a kind of electromagnetic wave. When it passes through a slit, such as a ball, it will change direction. This is a wave property. We call it diffraction. The other property of wave is even more interesting. For example, if we have 2 ping pong balls, we put them together, we will definitely see ping pong ball. 2 ping pong balls there, right? Because 1 plus 1 equals to 1, we will definitely see the 2 ping pong balls at the same position. But for wave, it's different. If we have 2 waves with the same frequency meet each other in the space, it will interact. What does it will interact? We can either get 1 plus 1 equal to 1, we get enhanced light intensity. We will say a bright ball, light is enhanced there. But we may also say 1 minus 1 equal to 0. When 2 beams of light meet each other in the space, if they are out of this, then we will see zero intensity. We cannot see any photon. We cannot detect any light there. Okay, this is a typical property of wave. Two particle meet each other in space, definitely there will be two. But two waves meet each other in the space, then depending on their phase difference, we can either get enhanced wave, enhanced magnitude, or reduce the wave, completely reduced to zero. Okay, so this is the property of wave. This is the first point you have to understand. And then the second point is, okay, when the wave, two waves meet each other, it will be enhanced or be reduced. Okay, this phenomenon is called interference. Okay, it's called interference. So that the interference of light, which means two beams of light meet each other in the space. Then depending on the phase difference or optical path difference between the two beams of light, we can either get the intensity of light there being enhanced or reduced. Okay, or reduced. And then the second point is here is when the intensity will be enhanced or when the intensity will be reduced. Okay, so that's the second point said. Okay, whether it will be enhanced or reduced depends on the phase difference between the two beams of light, or that can be translated into optical path difference of light. If the optical path difference of this two beams of light is always equal to an integer times the wavelength, an integer times the wavelength, so that corresponds to a phase difference is a multiple times 2 pi. In this case, the light will add up together to give us a bright spot. Okay, bright spot. So which means this is called constructive interference. Constructive interference means if we will get a bright spot. It also means the intensity of light will be enhanced to light add up. Okay, so the criterion here is the optical path difference is equal to an integer times the wavelength. In this case, we get the bright spot. Bright spot means constructive interference. Also means the intensity of light is enhanced to the maximum there. On the other hand, if their optical path difference, is a half integer times lambda, half integer which means an integer plus 0.5. Okay, if it's a half integer times lambda, then we will always get destructive interference. Destructive interference means dark spot. Also means the intensity of light will be reduced to the minimum there. That is called destructive interference. So as I said, light is a kind of electromagnetic wave. When two beams of light meet each other in the space, it can interfere. Either give us bright or dark spot, right? Whether it's bright or dark spot, depending on the optical path difference. Okay? Optical path difference equal to integer times lambda, we get a bright spot. Equal to a half integer times lambda, we get a dark spot, or we call dark fringe. Okay, these are the 2 points you have to understand. Now, the last one, the most important one is actually the summary. So that if you want to solve the problem of interference, then you refer to this summary. Okay, as I said, the problem of interference always asks you to equal the optical path difference either equal to n times lambda or a half integer times lambda. Because in the course material, we learned that there are 2 kinds of interference, either Young's double slit interference or the thin film interference. No matter what interference it is, okay, different interference will just give you, different calculation for the optical path difference delta L. Okay, for example, in Young's double slit, delta L is calculated in this way: d times sine theta. Okay, d is the distance between the 2 slits. Theta is the angular position of the slit. It also equal to d, the distance between the 2 slits, divided by the position of the dark or bright fringe, divided by the distance between the film and the 2 slits. Okay, and the Young's double slit, we can get the optical path difference either equal to 2nt or 2nt plus lambda divided by 2. So which means different interference experiment give us different calculation for the optical path. the optical path difference only given by the geometry. Okay, you can say the optical path difference is only given by the geometry. So the problem of interference normally asks you what kind of geometry in order for us to get a bright or dark fringe. What kind of geometry will give us the bright or dark fringe? So that what we have to do is to equal the geometry dependent optical path to either m times lambda or m divided plus half times lambda. So for example, if I say, okay, I have a simple experiment. So its optical path difference is given by this number. I want you to find out how thick the T it is in order to get a dark fringe. So that you will be able to say what I should do is to equal this 2nt to this guy, so that I will be able to find T. So as I said, all the problem of interference is summarized in this table. You should either equal the one of these three parameters in the second column to either m times lambda or m plus half times lambda. All the interference is doing this way. There is no exception. No exception. All the interference is equal the optical path difference. If the problem asks for bright fringe, we equal this optical path difference in the bright fringe. If this question asks for dark fringe, we equal one of these to the dark fringe. Condition. Always do the same. Always do this step. There is no exception. Okay. If you refer to your last video, refer to the summary lecture. All the procedure is summarized here. Let me repeat because it's so important. So important. Okay. Always equal the geometric dependent optical path in the second column here. So one of these three equations. To m times lambda if the question asks for bright fringe. Or I equal one of these, then depending on what experiment we are looking at, okay? To this guy, m plus half times lambda if the question asks for dark fringe. Any question? Any question? So no question on them. The last summary is regarding the thin film. So thin film, which means we have a film placed on a certain substrate, so that they can get enhanced or reduced reflection. And then for thin film experiment, the optical path difference can be calculated by either 2n or 2nt plus lambda divided by 2. So that now I will help you judge when to use this 2nt as delta L and when to use this 2nt plus lambda divided by 2 as delta L. So the only criterion is the refractive index of the film. Okay, is the refractive index of the film. If the refractive index of the film, okay, if the refractive index of the film is just fall between the refractive index of the bottom and the top cladding. So which means, for example, my silicon N here, its value just fall between this glass silicon dioxide. Its refractive index just smaller than the bottom refractive index, larger than the refractive index of the top. Okay, so this is what I mean. The film has a refractive index fall between the refractive index of the two cladding. In this case, my delta L is calculated at 2nt. In this case, it's calculated at 2nt. However, if the film's refractive index is larger or smaller than the two cladding, so for example, here I have a glass, top and the bottom are both air. So that glass refractive index are larger than both top and the bottom. Okay, then I use 2nt plus half. Or on the other hand, if I top and the bottom are glass, intermediate film is air. Air's refractive index is now smaller than both top and the bottom. I also use 2nt plus half lambda. Okay, so which means as long as my film's refractive index is both larger or smaller, okay, then we use 2nt plus half lambda as my delta L. But on the other hand, if my film's refractive index fall between the two claddings refractive index, bottom and top claddings, I use 2NT. So that if you now identify this is a thin film experiment, okay? For example, the intermediate film layer here, just the film between the top and the bottom, we use delta L. Let this delta L 2NT equal to m times lambda or half integer times lambda, depending on whether the question asks for bright or dark fringe. But on the other hand, if we are looking at this condition, you should equal this guy to this m or m plus half times lambda. Okay? So this is the whole procedure. Okay? So as I said, the most important concept is still, provided here in this table. So if no question, let's continue with our class. So tutorial question 1. Here we have a thin film of oil whose refractive index equal to 1.25 located on a smooth, wet pavement. So this pavement is water with a refractive index n equal to 1.33. Okay, so film's refractive index and the Clady's refractive index are both given. When viewed perpendicular to the pavement, the film appears to be predominantly red. So red light wavelength 640 nanometer and has low blue color. So blue color is 512 nanometer in wavelength. The question wants us to determine how thick is the oil film. As I said, clearly this is a thin film experiment. Okay, this is a thin film experiment. Okay, so as I said, for thin film experiment, we should always try to equal, interference, try to equal the optical path difference in either m times lambda or half integer times lambda, depending on whether the question asks for bright or dark spot. But this question does not directly tell us whether I want you to look at the bright or dark fringe, whether it's constructive or destructive interference. But it actually indirectly tells us, some information. The film appears to be predominantly red. What does that mean? That means for red light, the reflection is bright or dark fringe. The film appears to be predominantly red, which means for red light, I should say a bright fringe for the red light. So that is intensity is enhanced, right? Bright fringe, which means intensity is enhanced. Predominantly red, which means white light illumination. Red light is enhanced. So that the red light is enhanced. I say bright fringe for the red light. Then how about the blue light? Low blue color means what? The blue fringe. The blue color is dark or bright fringe for blue color. Low blue color here is what? Yes, very good. Which means we can say low blue color, which means this is destructive interference. We cannot say the intensity. It's 1 minus 1 to there. Okay, it's destructive interference, it's a dark fringe. So which means the thin thickness of the film, it will give rise for bright fringe for red color, while dark fringe for blue color. Okay, so this is what this question tells us. So the thin thickness, because the thickness of the film here is fixed, this thickness will cause dark fringe for blue color, while bright fringe for red color. Now the refractive index, you can say N1 equal to 1, N2 1.25, N3 1.33. So N2 is just in between N1 and N3. So that's my optical path difference equal to how much here? Should my optical distance equal to how much? 2NT or 2NT plus lambda? Yes, very good. In this case, my optical path difference should be equal to 2NT. So if we set, the wavelength here to be red light, this 2NT should equal to m and integer times the red light wavelength, right? Now if we set the same delta L 2NT, because 2NT the optical path difference is the same for different color of light. But because the wavelength change, if the wavelength now change from red to blue, which means now this 20 should equal to 1/2 integer times the blue light wavelength, right? Because it's bright fringe for red, dark fringe for blue. Okay, so which means the same number, the same optical path difference equal to an integer times the red light wavelength equal to 1/2 integer times the blue light wavelength. Okay. So that you can say the same distance. So which means my m times red light equal to 1/2 integer m plus 1/2 times the blue light. So that I get this condition, okay? Red light's wavelength times m1 equal to blue light's wavelength times m2 plus, so this is another integer plus 1/2. If you rearrange this equation, you can get 5 divided by 4 equal to 2m2 plus 1 divided by 2m1. So if we equal the denominator with the denominator, numerator with the numerator, you can get m1 and m2 are both equal to 2. Okay. So that you determine the number of integer m1 and m2. You substitute one of them back into this equation. You can get what is the thickness T. It's just about 512 centimeters. Okay. 512 centimeters. Any question? Any question? Any question here? Okay, if no question, so that let's look at the question 2. Okay, so here I have a beam of wavelength equal to 580 nanometer passing through two closely spaced glass plates. Two closely spaced glass plates. The question wants us to determine for what minimum zero value of the plate separation, so that the transmission light is bright. So this question means what we want is to enhance the transmission. So you can say for the figure already tells us what are the two beams we are looking at. The beam 1. Yeah, hello. Yeah, any question? Any question? Okay. So if no question, you can directly see from the plot of the figure why we can have the interference of light at the transmission side, because there are two light interference. The first beam of light is a light that is transmitted directly through the two slabs. The second beam can respond to the light that is transmitted, okay, that is reflected at the first interference, that experience two reflection before, transmitted through the light. So which means the second beam of light, ray 2 will first transmit to this interface, get a reflection here. Then it will be reflected the second time at this interface. Then it goes back, to the transmission side. To the transmission side. Okay, so this is how light is goes for ray 2. You can say because ray 1 directly goes through, ray 2 experience reflection up twice. Of course, the optical path difference between ray 1 and ray 2 are different. Why it is different? So first, their optical path difference within the air gap is different. For example, outside this, this separation, ray 1 and ray 2, their optical path difference are all the same, right? They experience the same optical path difference because optical path difference is equal to the refraction index times the phasal path. So outside, the refractive index and their phasal path are the same. So for example, in this blue region, the refractive index and the phasal path for ray 1 and ray 2 are all the same. So what's different only happens within this gap, okay, within this separation. Ray 1 only passes the separation once. How about ray 2? Ray 2 passes the separation how many times? You can say ray 2 passes the separation how many times? 1 times, second times, third times, right? Ray 2 passes separation. First passing through, then reflect back, second time, and then go through it again. Ray 2 experience this separation 3 times. So that their physical path difference is actually 2nd. Okay, is actually 2nd. Okay, it's just a 2D because 3D minus 1D equal to 2D. And also we to experience some reflection. So as I summarize in my summary slides, light may or may not experience any phase change upon reflection. So if light is reflected in the low index material, it will experience a half lambda additional optical path because this phase will be changed by pi. So for example, here my light is reflected at this air glass interface. Air is a low index material, so that at both surfaces, my light will experience pi phase shift. Pi phase shift can respond to a half lambda additional optical path, but experience 2 times pi phase shift, so that is in total 2 pi phase shift. 2 pi is equal to 0 in the complex plane, so which means we don't have any additional phase shift. We don't have any additional phase shift. So that the optical path is just this 2nd. N is the reflection index of the air, which is 1. Okay, reflection index of air, which is 1. This is my delta L. As I said, once you determine the delta L, you should set this delta L to be either lambda times n or lambda times n plus 1/2. Okay, depending on whether this is bright or dark fringe. So this question wants us to enhance the transmitted light so that I want this equal to bright or dark fringe condition. I want this delta satisfy bright or dark fringe condition. So, or am I looking at the bright or dark fringe for transmitted light? Any idea? Any idea? The question wants us to enhance, right, the transmitted light. Want the transmitted light to be bright. So of course we are looking at constructive interference for the transmitted light. We are looking at the bright fringe. So that I should set my 2nd equal to m times lambda. Equal to m, so m times lambda. The question asks for m is an integer, okay? The question asks for what is the minimum thickness d so that I transmitted light will be bright. So that which means my m equal to 1, 2, 3. So it can all the d get there can satisfy the bright fringe condition. But for the minimum thickness, I should set my m equal to 1. Okay, I should set the m equal to 1. If I set m equal to 0, okay, d equal to 0, that is not a non-zero thickness. But if I set m equal to 1, this is a minimum non-zero integer. Okay, so that I can get the minimum non-zero thickness for my bright fringe. So in this case, my d equal to lambda divided by 2, which is 290 nanometer. 290 nanometers. Okay, any question? So if no question, now I have a question for you. So this is a question I delivered underneath catalytics. Okay, again, I have a thin film of oil floating on water. I want you to determine what is the minimum non-zero thickness of the oil that will strongly reflect the green light. So I want you to strongly reflect the green light, which means I'm looking for bright or dark fringe for green light. Sorry, bright or dark fringe for green light. Any idea? Bright, very good. So that you just apply what I talked about just now to calculate. Okay, I give you 3 minutes to submit your answer by the catalytics. Okay, 3 minutes. 3 minutes to submit your answer on the catalytics. So last 1 minute, try to submit your answer. Yeah, try to submit your answer underneath analytics. Okay, due to the limitation of time, so that I will show you the answer, show you a solution. Okay, so yes, we should choose D. So first, how much should be my optical path difference? How much should be my optical path difference? The thin film is oil reflecting index equal to 1.25 is in between water and air, right? It's in between water and air, so that my delta L should equal to 2NT. 2NT. I am looking at bright range because strongly reflected green light. So which means for green light, I'm looking at the bright range. So that should equal to M times lambda. Again, minimum non-zero is M equal to 1. Minimum non-zero is M equal to 1. So that T just equal to lambda divided by 2N, which is 212 nanometer. 212 nanometers. Okay? Any question? So I should choose D. So now, so in the next, you know, I will talk about some past examination data related with this thin film. Okay, related with this thin film. Okay, so the first question was tested about 4 years ago. Here I have a camera lens with a refractive index equal to 1.52, coated with anti-reflection coating. Whose coated with an anti-reflection coating. Okay, and this is a camera lens which is substrate. The anti-reflection coating has a reflecting index 1.25 in order to minimize the reflection of visible light at this wavelength, 430 nanometer. I ask what is the minimum thickness of this anti-reflection layer. So I want to reduce the reflection, which means I want this wavelength to be bright or dark fringe. Very good. I want this to be dark fringe. So which means I should set my delta L equal to half lambda times half integer times lambda. So now this is a configuration we are looking at, still a thin film experiment. Top cladding is air. This is the flow rate, okay, reflecting that's 1.25. Lens reflecting index 1.52. So you can say the thin film reflecting index is still between the top and the bottom cladding, which means my delta L here should be 20. Okay, my delta L should be 2, and N is the reflecting index of the thin film. So that my delta L should be 2N2 times T. This is delta L. I am looking at dark fringe. Okay, I am looking at dark fringe. So that I should set this delta L equal to a half integer times lambda. Half integer times lambda. Now, okay, we can set M equal to minimum integer 0. Because when I set M equal to 0, my 2NT equal to lambda divided by 2. That can still give me a non-zero thickness. Okay, anti-reflection coating requires this delta L equal to half integer times lambda. So here, because it's a half integer times lambda, the minimum half integer is 0.5, 1/2. Okay, is 1/2. Minimum half integer is 1/2. So that I get my delta L, delta T just equal to this lambda divided by 4M, which is 86 nanometer. Okay, 86 nanometers. Any question? Any question? Yes.
How do you know minimum thickness actually equals 0? Does the N value change responsibly?
The N will not change that. the minimum value, which means my m can be set to any integer, for example, 0, 1, and 2. Because it wants my t to be the minimum, so only m equal to 0 can give us the minimum here. Because if m equal to 1, then it equal to 1 and so 3 divided by 2. 3 divided by 2 will make t larger, right? So I only set m equal to 0, so that because as I say, it's half integer, m plus 1/2. You want to minimize this, so that I set m equal to 0. So actually, my m equal to 1, 2, and 3, it will both give us an anti-reflection coding. But the question asked for the minimum thickness. The minimum thickness, so that I should choose the minimum m. So the minimum m is 0.
So the m value has to be always more than 0.
Yes. It can be 0, 1, 2, 3. 0, 1, 2, 3, yes, because t is positive now. It can be 0, 1, 2, and 3. So that for this case, you want to minimum, the minimum thickness, you choose m equal to the minimum integer, which is 0. Okay? So there are some more questions, but I think you can take a look by yourself, okay? So that I will not talk about in very detail. For example, the question in academic year 2017, you can find the solution yourself, on my slides. Or 3 years ago, semester 2. So this question I will not talk about in detail. So what I will talk about in detail is this one. Okay, so here I have an unknown material placed on silicon. When light with a wavelength of 800 nanometer incident from air onto an unknown material, it reflects constructively. Okay, it refracts constructively. So this unknown material is a thin film placed on a silicon substrate. Given that the silicon has a refractive index equal to 3.7, I want you to determine if the refractive index of the unknown material is larger or smaller than that of silicon. And then assume the unknown material thickness is 100 nanometer. Okay, so that this is the configuration we are looking at. We have a 100 nanometer thick thin film of an unknown material. When light incident upon this thin film configuration, it will refract light constructively. As said, it will reflect light constructively. I want you to determine whether this unknown material has a reflecting index larger or smaller than silicon. Okay? So that's what we should do is, okay, we can just assume, okay, first this reflecting index is smaller than silicon, and then we get some condition and say whether the condition we get conflict with any, for example, law of physics or conflict with our original assumption. Or we said this material has a reflecting index larger than silicon, then whether that makes sense or it will also conflict with some conditions. So now let's first assume this unknown material has a reflecting index smaller than silicon. So smaller than silicon, which means the unknown material's reflecting index is in between the bottom and the top gradients. It's just in between the top and the bottom gradients. Then my delta L should equal to 2nt, right? My delta L should equal to 2nt, right? 2nt constructive interference, which means I should let my delta L equal to an integer times lambda. Then I equal 2nt equal to m times lambda. Okay? Reflecting index n, of course, unknown, but t and lambda is given. T and lambda is given. So if I substitute t and lambda into this equation, you can get my n is always equal to 4 times n. Okay, my reflective index is always equal to 4 times m. As I said, m is an integer, can only be 0, 1, and 2. Of course, for m equal to 0, my n equal to 0. Okay, there is no reflective index smaller than 1. Okay, no reflective smaller than 1. And then the only possible reflective index is from m equal to 2. So which means my n should be larger than 4. In this case, I get my n. The minimum n is 4, but the minimum is 4 conflict with the assumption that the material has a reflective index smaller than silicon, because silicon's reflective index only 3.7. So that this n equal to 4m conflict with that my original assumption that the reflective index of the unknown material is smaller than silicon. So that this is wrong. Then we check if the material has a reflective index larger than, okay, has a reflective index larger than silicon, whether we can get some condition makes sense. If this unknown material has a refractive index larger than silicon, okay, so which means in this case, my thin film has a refractive index, the maximum refractive index, so that my delta L should be 2nt plus half lambda, okay? Should be 2nt plus half lambda. And then construct inference set this guy equal to m times lambda. So that you substitute t and lambda into this equation, so that you can get now my n is 4m minus 2. 4m minus 2. You can say when my m changing from 1, 2, and 3, my n is now larger than 1. Okay, so makes sense. You can say with m larger than 2, my n will now be larger than 6. That agreeing with our original assumption. That the unknown material has a refractive index larger than silicon. Therefore, we conclude that this unknown material's refractive index should be larger than silicon. Okay, the unknown material's refractive index should be larger than silicon. Any question? Any question here? Okay, so if no question, we will come to tutorial question 3. Okay, so this is also one of the most important questions. Okay, for Newton's ring. Okay, this kind of question is called Newton's ring tested quite often, in the final examination. So here we have a plano concave lens with refractive index 1.5 placed on a glass substrate, so that it will film an air gap, between the lens and the glass plate. So the question said, okay, the radius of curvature for this guy. So this radius of curvature for this surface is 8 meters. Light is illuminated with from above with a wavelength given by this number. Then we see a series of bright and dark fringe. Okay, the interference pattern is such that a dark spot is formed at the center. Then, so in the center we have a dark spot surrounded by 50 dark rings. So the question wants us to determine what is the thickness of the air layer at the center. So the thickness of air here, and then calculate the radius of the outermost ring. So which means what is the radius here, and then find the focal length. So which means for this configuration, okay, when we look for the top, you will see actually a series of bright and dark fringe in this form. In the middle, we see a dark spot surrounded by 50 dark rings. So which means in this case, the variation of this air gap will form a series of bright and dark fringe. Will form a series of bright and dark fringe. Why is that? We first have to understand this question. Okay? We first have to understand the question. Okay? Because of the curved surface, here we have an air gap. Okay, with its thickness changing at different position. Okay, changing from there for a maximum thickness at the center. So that the thickness here is variable. We know that for thin film, especially for this kind of thin film, at each different position, the air's refractive index is in between glass, the two top and bottom gratings. So which means my optical path difference delta L should be equal to how much? So you see this question may be quite difficult. Sometimes if you first look at this question, you don't know how to solve that. But what I can tell you here is, okay, this is a Newton's ring experiment. It's similar to thin film experiment. For thin film experiment, as I said, we should always write on delta L equal to half integer or integer times lambda. Now for this question, what is my delta L? 2nt or 2nt plus half? Very good, it should be 2nt plus half, because my reflection happens at the interface of the air. Air's refractive index is between the two bottom, the top and bottom gratings. So that my optical path is 2nt plus half. The question all talk about dark fringe, dark rings. So which means we are looking at dark fringe. So that I set my delta L equal to half integer times lambda. Cancel out this half lambda. I get, okay, the dark fringe condition is 2nt equal to m lambda. Okay, dark fringe condition equal to 2nt equal to lambda. So that this tells us a very interesting story. Okay, you can say, when I change t, right? When I change t, I will change my optical path difference, right? yt here will change the optical path difference. The optical path, so my t changes from 0 to a finite number, which means my optical path difference also changes from 0 to a finite number. So which means if my optical path, is changing from 0 to the center, I may be able to repeatedly satisfy the bright and dark fringe, right? Maybe at one thickness, for example, at t equal to 0, I satisfy the dark fringe condition. At another small thickness, I can satisfy the condition for bright fringe. When t increase, I may be able to satisfy the condition for the, another dark fringe. So this is why I will say some figure like this. Is because when I go from the red to the center, the thickness of the air of the intermediate film is changing. Okay, become larger and larger. Then I will repeatedly satisfy the bright and dark fringe condition, so that I will get this series of dark, bright, dark, bright, dark, bright fringe. Okay, so this is why we say Newton's ring, because the changing of this, air thickness, my optical path difference repeatedly satisfy the bright and dark fringe condition. Okay, any question? Any question? So you can say, of course, at the edge, my t equal to 0. At the edge, my t equal to 0. T equal to 0, which means my m equal to 0. I see the first dark fringe, exactly as what this question tells us, okay? At the outer edge, I have the 0th order dark fringe. Okay, the first dark fringe is a 0th order dark fringe. And then when I change the thickness, for example, another t, I may satisfy m equal to 1. M equal to 1 is the first order dark fringe. M equal to 0 is a 0th order dark fringe. M equal to 1 is the first order dark fringe. Okay, and then become larger, m equal to 3, I get the third order dark fringe. Okay, the third order dark fringe. So that the first at the middle, I also get a dark fringe because I am the dark small. As long as I will be able to understand what is the corresponding m at the middle, okay, m times lambda divided by 2n will give us what is the thickness there. So which means no matter at what position, as long as I know what is the corresponding order of the dark fringe, I will be able to calculate the corresponding thickness at that position. So now, if you want to calculate, the thickness at the center, what the question asks for is to first calculate the thickness of air at the center. We first need to know what is m. So as I said, when we go from the center or the edge to the center, the thickness is gradually increasing. So that you will, at the edge, you will first satisfy the first order dark fringe, 0 times lambda. Another position, I will become, this 2nt will become 1 lambda. So that is the first order dark fringe. Then repeatedly, it will become 2 lambda, 3 lambda, and 4 lambda. The question tells us, okay, at the middle dark fringe, it was surrounded by another 50 dark rings. So which means at the middle is so what's the order for the middle dark fringe? At the middle, what is the order? It should be 50, right? Because only when it is 50, then for the dark fringe smaller than it is 0 all the way to 49. There are just 50 rings surrounded by this 50 dark fringe, okay? From 0 to 49. The 0 is the first dark fringe at the outer rim, and then first dark fringe, second one, first order dark fringe, second order dark fringe, third order dark fringe. From there, 0 order all the way to 49th order. Okay, it is surrounded the 50th order dark fringe at the center. So which means at the middle point here, it should correspond to my 50th order dark fringe is a 51st dark fringe, okay, surrounded by another 50 dark rings. So which means in this case, at the middle, the order m should be 50. Then 50 times lambda divided by 2n will give 50 times lambda divided by this 2n, n of course is equal to 1. I can get the thickness at the center, okay? I can get the thickness at the center. Any question here? So if you know this is the most difficult part. If you know this, I think then the question is more or less solved, okay? So that's the second question want us to determine what is the radius of the lens. Okay, this guy. I give it the radius of curvature equal to 80 centimeter or 8 meters. Now I get this T already calculated from part 1, okay, part A. So that if we look at this right angle, AB is equal to 8 meters. AC is equal to my radius of curvature minus the thickness T, right? 8 meters minus T. So which is this guy, 8 meters minus T. So that if you look at this triangle, AB and AC can be both calculated. So that you apply the Pythagoras principle. My BC square equal to AB square minus AC square. You can get my BC is about 1.53 centimeter. 1.53 centimeter. Okay, just from some mathematics, no physics. So only physics is from part A. So that's part C. I want you to get the focal length. The focal length of this guy. So you can say part C is actually more or less unrelated with part A and part B. Directly testing to apply the equation of the Lance-Vickers equation. Okay, so you can say in the final examination, maybe you found the question may have a number of sub-questions. Maybe the first or the second question is very difficult. But maybe the last one is completely unrelated with part A and part B. Part C, maybe you can directly get that by directly applying some certain equations, you can get the answers. Then this is the case for this question. Because the question already gave us is a planar concave length. Planar concave length, which means for planar surface, okay, its radius of curvature is infinite. And this BC radius of curvature is equal to 8, so that you directly apply Lance-Vickers equation, n minus 1 times R1 divided by R1 minus 1 divided by R2. As I said, R1's refractive index is infinite. R2 is 8 centimeters. Refractive index already given by the question, so that you directly submit the parameter into this equation, you can get my F is minus 60 meter. Minus 60 meter. Okay, this is the solution to this question. Okay. You can say this is really easy. Directly apply Lance-Vickers equation, you can get the right answer. So in the future, if you see some question in the final evaluation, if you found part A or part B, part B, you don't know how to solve. But do remember to also look at part C. Maybe part C will be very easy, completely unrelated with the previous part. Okay? Any question? Any question? Okay, so if no question, let's look at the one past examination papers. Okay, so here again, consider another planar convex lens placed, in the configuration shown below. So here we have an air gap. Okay, air gap from here. So from the center to the edge, the thickness is gradually increasing. Okay, it's gradually increasing. So that this curved surface and this thin film and this bottom surface here will cause thin film interference. Will cause a full reflected light and thin film interference. Okay, so that's the question said. Okay, I have wavelength of light 500 nanometer incident. Normally to this configuration. Incident to the configuration. The radius of the second dark ring or the third dark fringe from the center of the lens is measured to be 2 millimeters. Assume that the lens and the glass have a refractive index equal to 1.5 and the convex surface is a spherical. I want you to determine the radius of curvature for this lens. And then if I still use this lens, but I fill this air gap with a refractive index equal to 1.4, I want you to recalculate what is the radius of the second dark ring. Okay. I want to what is calculate of the third dark ring, okay, of the third dark range, okay. Assume the radius of curvature is still the same as 1. So now let's look at what this question means. As I said, for this thin film interference, the interference of light just comes from reflection at the two interface of this air gap. At the two interface of this air gap, because air's reflective index is smaller than most, top and bottom glass platings. So that my delta L should equal to how much? My delta L should equal to 2nt plus half lambda, right? Because its refractive index just in between the top and the bottom glass is 2nt plus half lambda. The question again asks for dark range. I should let this delta L equal to half integer times lambda. Okay, so m plus half times lambda. Cancels out this half lambda. My 2nt should equal to m times lambda, right? Any question? My 2nt should equal to m times lambda. Cancel out this half lambda. Okay? So now the question tells us, okay, the second dark ring or third dark fringe, the second dark ring or third dark fringe should occur at m equal to 2, right? M equal to 0 is the first one, m equal to 1 is the second one, m equal to 2 is the first one, okay? Because m equal to 0 is the dark fringe is a dark tone. So that my second dark ring can respond to the third dark fringe, which is m equal to 2. M equal to 2. So that the second dark range I'm looking at is my m equal to 2. I set m equal to 2 here, m equal to 2 here. I can get my t. The thickness, okay, the thickness of air gap at that position is equal to t equal to 500 nanometer. Equal to 500 nanometer because n here is equal to 1. N here equal to 1. Okay, so that I get the thickness of this air equal to 500 nanometer. You can say thin film normally want us to calculate what is the thickness of the film in order for dark range or bright range to happen. Okay, so you can say here again I get t equal to 500 nanometer for the third dark fringe, second dark range to happen. Okay, now you look at this right angle. The radius of curvature is given. Once you get t, you will be able to know what is the length of this edge, r minus t. This is, okay, this is 2 millimeter. This is 2 millimeters, okay? So that I can quickly get what is R, because R is unknown, okay? R is unknown. Then I apply again this Pythagoras principle. R squared minus R minus T squared should equal to 2M squared. So rearrange this equation, you can get my R is about 4 meters, okay? My R is about 4 meters. So once you get R, the second question says I keep this radius of curvature unchanged. I fill this with water. What will happen? You fill this with water. Water's refracting index is 1.4. 1.4 is still smaller than the refractive index of the glass. So that my delta L will remain unchanged. My delta L will remain unchanged. I am still looking at dark fringe. So that my condition for this dark fringe still remain unchanged as 2nt equal to m times lambda. Okay, still remain as 2nt equal to m times lambda. So that what changes is only the refractive index of this layer, the refractive index of this layer. So that my dark fringe is still 2nt times m lambda. I'm still looking at the third dark fringe, second dark ring, so that my m is set equal to 2 times lambda divided by 2m. Now I can get my thickness t was changed. Okay, thickness t was changed to 357 nanometer. Okay. Yeah, hello? Any question? So my t here is 357 nanometers. 357 nanometers. Okay. So now if you now look at this triangle again here, this triangle again, R is given fixed at 4 centimeters, T is given. It wants us to find the radius of this second dark ring, so you should change this 2 millimeters to what we want, okay? To, for example, this R3, this R3, okay? So that's the idea is you're looking at this right angle. This is R4 nanometer remain unchanged. This R minus T, T prime is given here, so that you know the edge length, 2 edge lengths of this right angle. So then from the Pythagoras principle, you can get what is my R3, which is 1.69 millimeter. 1.69 millimeter. Okay? Any question? Any question? So if no question, so of course we have some other question for the Newton's mean experiments, okay? But I don't have time to go through, so that you can take a look at your solution yourself, okay? So now I will come to tutorial question 4, okay? I will come to tutorial question 4. sorry. Before I go to tutorial question 4, I will talk about another passing examination paper, tested, 1 year ago in 2020. Okay, semester 1. So the thin film, the gradually tinted thin film apart from rotation, we also have this triangular effect. Okay, triangular edge, you can see it will also has a reflective index, changing from 0 to infinite thickness. So that for this triangular wedge, we will also be able to see a series of bright and dark wedge. This is also how thin film will be tested in the past examination papers. Okay, so this is related with tutorial question 4, but it's easier, so that I will first talk about this question. Here, consider a triangular wedge formed by 2 glass plates and a thread as shown in figure 1. So that the edge is filled with reflective. The wedge is filled with water whose reflective index is 1.33. The glass plates, the total length here is 5 centimeters long, and the thickness of this thread is 0.1 millimeter. So that with this 0.1 and 5 centimeters, I will be able to calculate what is the angle theta here. Okay, it's tangent theta equal to 0.1 millimeter divided by 50 millimeter. Okay, so tangent this angle equal to 1 divided by 50. Okay, 1 divided by 50. Okay, so when the wedge is illuminated by a single frequency light with a wavelength of 600 nanometers from vacuum, the interference fringe will appear. Why we will say interference fringe is because the thickness is changing. So that is similar to the Newton's ring. When the thickness T is changing, the optical path difference will repeatedly satisfy the bright and dark fringe. So that we will see a series of bright and dark fringes, upon the reflection at the reflection part. Okay. The question wants us to determine the distance of the second dark fringe. Okay. The second dark fringe to the contact point. Then find out what is the distance of the second dark fringe from the contact point if the water is drawn out and replaced with air. So again, first, water reflecting index is smaller than the reflecting index of glass. So which means my intermediate layers reflecting index is smaller than both plates reflecting index. My delta L should equal to how much? My delta L should equal to how much? 20 plus half lambda, right? Because its reflecting index is smaller than both cladding. Again, I'm looking at a dark range. I should say that this delta L equal to half integral times lambda. Again, I cancel out this lambda divided by 2, so that this dark fringe condition can be simplified as 2nt equal to m times lambda. 2nt equal to m times lambda. Okay? The question said, okay, we are looking at the second dark fringe. The first dark fringe, as you can see, happens at m equal to 0, right? Because m can be any integer, 0, 1, 2, 7, okay? The first dark fringe happens at m equal to 0, so which is t equal to 0, so which is exactly at the edge. This is the first dark fringe, exactly at the edge. So that the second dark fringe should happen at m equal to 1, should happen at m equal to 1 somewhere here. So that you set m equal to 1, you will be able to calculate what is the thickness of air at the second dark fringe, which is this 226 nanometer. But what this question wants is not the thickness of air at the second dark fringe. It wants us to calculate what is the distance between the second dark fringe to the contact point here. So you can say the thickness of the dark fringe, the thickness of the dark fringe T divided by the distance from the contact point x. So for example, we assume the second dark fringe happens somewhere here. Its distance to the contact point is x. So that my 226 nanometer, okay, so which is the thickness of this air, divided by my distance x should equal to tangent theta. As I said, this tangent theta can already be calculated by the geometry of this triangular edge, whose height is 0.1 millimeter, length is 5 centimeters, so u is 1 divided by 50. So that from this equation, you can get my x is about 0.11 millimeter, okay? 0.11 millimeter. Then, if this question was changed to, for example, another one, reflecting index become 1, okay? Reflecting index become 1, so that all the conditions remain unchanged. We are still looking at this. we only change this n equal to 1. Okay, change this n equal to 1. If you change n equal to 1, then the thickness of air will become to about 300 nanometer. Okay, 300 nanometer. Once T becomes 300 nanometer, so that with the last equation, I use 300 nanometer divided by x, which is tangent theta, so that I can get now my x is equal to 0.15 millimeter. So which means if now I replace this water with air, I will find my second dark fringe shift farther from the contact point. Okay, my second dark fringe will be shifted farther from the contact point. So any question here? Any question? So no question. Let's look at tutorial question 4. So here we have two glass plates and a thread, again from a triangle wedge. Okay, so this length here is 10 centimeters, while the thread is 0.05 millimeter in diameter. So which means this height D is 0.05 diameter. When the wedge is illuminated by two wavelengths at blue light 400 nanometers and the red light at 600 nanometers, I will see a series of bright and dark fringe. So actually, I will see a series of bright and dark fringe for red and blue light simultaneously. And their bright and dark fringe patterns are different. Their interference patterns are different. I want you to determine the distance of the second dark fringe from the contact point of the two glass plates. What does this mean? Now I illuminate this edge with two color lights. Because of the wavelength is different, both colors will form interference pattern, give us two different bright and dark fringe. A dark fringe, actually, a real dark fringe means there is no light, neither blue or red. But blue and red light, they have different interference pattern. If we are looking at a dark fringe for blue light, but that is not dark fringe of red light, so that we will see red color. This is not a pure dark fringe. On the other hand, if we are looking at the dark fringe for red light, but this dark fringe position is not the dark fringe position of blue light, and then we will see still blue color. This is not a pure dark fringe. So if you want to see a purely dark point, which means this point should be simultaneous the dark fringe for blue and red light. So which means we want, when we set, for example, this dark fringe condition, we want the standard thickness of air, it can satisfy the blue light and the red light dark fringe condition simultaneously. This is what this question asks for. Okay, so what we are looking at is this one. Again, we are looking at air between two glasses. So that's the dark fringe condition is 2nt plus half lambda, right? Equal to m times half lambda. Cancel out the m, so that 2nt equal to m times lambda is the bright fringe, is the dark fringe condition. So that the thickness of air is fixed at a certain position, so that's the optical mass difference is fixed. If this guy only satisfies m times lambda equal to, for example, if this only satisfies m times the blue light wavelength, so which means this is only the dark fringe for blue color. If this satisfies m times lambda equal to red light, so which means this is a dark fringe for red color. Okay. But if we want to say a pure dark fringe, I want this lambda is simultaneously. Okay, here is simultaneous the dark fringe for blue and red light. So which means I want this delta L here. I want this delta L equal to 2nt equal to an integer times the blue light wavelength is also equal to another integer times the red light wavelength. I want these two conditions to be simultaneously satisfied. Because both m1 and m2 are integer, you can say, okay, my delta L should always equal to a multiple term, should be the common multiple of 400 and 600. Okay, then the smallest t should equal to the least common multiple of 400 and 300. So which is 1020. Okay, so here if we have two colors light, my 2D should equal to the common multiple of 400 and 600. Then if it's a final examination, attention here, if it's a final examination, what I asked is okay, I have 3 columns of line. For example, I add another 800 parameter here. Then what you should look at is a common multiple for 400, 600, and 800 simultaneously. Okay? If you want to find the dark range for 3 colors, okay, I need my data node to be the common multiple of that 3 wavelengths. So, of course, if I have 4 wavelengths incident on this wedge, I want to find the pure dark range. And then the series of the air for the dark range to happen is a common multiple of the 4 wavelengths. It's always like this. Because the question asks us to find out the first, or dark fringe. The second dark fringe is, of course, M1 and M2 equal to 0. Then the first dark fringe is the least common multiple. Is the least common multiple, which is 120 nanometer. So that you set this to 120 nanometer, then you can get a T to about 600 nanometer. Then once we get a T equal to 600 nanometer again, what we want to find out is the distance to this edge. The distance to this edge, of course, is 600 divided by x equal to tangent theta. Tangent theta is also 5 millimeter divided by 10 centimeters, so that I can get my x equal to 1.2 millimeters. Okay, 1.2 millimeter. Any question? Any question? Okay, so no question. Let's look at the last, tutorial question, the last example. Okay, of course, here we have some past examination papers, but here I don't have time to go through. You can take a look yourself. Okay. Again, this is illuminated by 2 different wavelengths, 450 nanometer and 600 nanometer. Then I want you to find out the distance, okay, of the third dark fringe to the glass edge. So here I want you to find the least common multiple of these 2 wavelengths. Okay, you take a look at the solution yourself. Then before I continue to the last part, okay, so let's first try an example. Here I have experiment, in the double slit. What I want to ask is, okay, the distance of adjacent bright fringe. So that I want to increase the distance between adjacent bright fringe will be increased by what? By which one of the following? Okay, by which one of the following? Remember, the optical glass difference delta L equal to D times Y divided by L. L is the distance between the film and the 2 slits. Okay, so I will give you 2 minutes to try, and then submit your answer via learning catalytics. Question already delivered. Okay, use 2 minutes to choose to submit your right answer. So another 1 minute left. Try to quickly submit your answer. Okay, thumbs up. Okay. So for this question, okay, for this question, as I said, what we are looking at is this Young's double slit experiment. Okay, Young's double slit experiment. So what we should do is, set the optical path to bright fringe m times lambda. So for example, if the first dark fringe we are looking at has an order equal to m, then its neighboring bright fringe should be equal to d times y2 times another integer, neighboring integer times lambda. Okay, so y1 is the position for the mth order bright fringe. Y2 is the position for the m plus 1th order bright fringe. Okay, as I said, always set delta L equal to the bright or dark fringe condition. So that from this equation, you can get what is the position for y1. The mth order bright fringe is m lambda L divided by d. Y2 is m plus 1 lambda L divided by d. So that their distance is y2 minus y1, always equal to lambda times L divided by d. Okay, lambda times L divided by d. Lambda is the wavelength. L is the distance from the screen to the two slits. D is the separation between the two slits. Okay, so this equation is very important, but unfortunately, it will not be provided in your formula sheet. So the optical path difference, d sine theta equal to m times lambda, will be given in your formula sheet, but this one will not be given. But as I said, it's very important. I would suggest every of you try to remember this formula, or you remember the approach to determine this formula. Because in the quiz, you may be referred to a certain question. How can I increase or reduce the distance between the neighboring bright or dark fringe? Okay, similar to this one. So you can say here we have several approaches. We can increase or decrease lambda. How to say? We put this double slit experiment from air to water. If you do that in the water, the wavelength will be smaller, right? And then the neighboring bright fringe or dark fringe will be reduced. Or you can also change the distance or change d in order to change the bright fringe position. So what we should do, what we want to do is to increase the distance. Increase the distance can either be done by decrease the distance between the separation between the two slits, or we increase the wavelength. So that we should choose B. Either decreasing the slit separation or increase the wavelength. Do we have a third approach here? Do we? The question only tells us how to change the wavelength or decrease or increase the separation. Do we have a third approach to increase the separation between the two slits or the wavelength? We can also increase L, right? Increase L, which means we make this screen farther from the two slits. That can also change the separation between neighboring bright or dark fringe. Okay? So this is the third approach, which we not talk about here. But in the quiz, you may encounter similar question. Okay? So final example. So here we have a double slit experiment conducted with a laser source at 540 nanometer wavelength. The two slits are separated by a distance. Okay, this separation here is 4 millimeter. A thin glass plate is then placed in front of one of the two slits. So a thin glass plate only placed in one of the two slits, such that each bright fringe will just move to the location of the adjacent bright fringe. Okay, each bright fringe will move to the position of the adjacent bright fringe. I want you to determine the thickness of this glass plates, given that the reflecting index of this glass is 1.56. Okay. Now let's look at what this. First, you have to understand this question. So here we are looking at a thin film double slit experiment. Before we insert this glass plate, of course, a series of bright fringe will be formed on the screen. So for example, if we assume this is a series of this bright fringe pattern, interference pattern. This is before we insert a glass plate, on the bottom slit. Now, after we insert this glass plate on the bottom slit, what will happen? The position of this bright fringe will move. Okay, but it will move in such a way, it will just move a little bit down. causing the position of the zeroth bright fringe become the position of the first bright fringe. This is what this question asks for, okay? Because it will just cause the bright fringe to move to the neighboring bright fringe. So which is originally at the center, we have zeroth order bright fringe. Now it will change to the first order bright fringe. This is what this question tells us. Okay, this is what this question tells us. Now if we just look at the zeroth bright fringe, so which means originally at the center, we are looking at the zeroth order bright fringe. Optical path difference delta L should equal to how much? Optical path difference for the zeroth bright fringe equal to how much? You give me that zeroth bright fringe delta L, m times lambda when m equal to 0, delta L equal to how much? 0. Very good, 0. So which means before we insert the glass, this position will cause zeroth optical path for the two light ray. Now after we insert the glass, m become 1, which means the optical path difference become how much? The some position optical path difference become how much? Lambda, right? Because m become 1. Right, delta L equal to m times lambda. So the same position before and after insert the glass, my optical path difference will change it from 0 to 1. So this is actually what this question indirectly tells us. Which means before we consider if we consider the zeroth bright fringe, before we insert the glass, delta L, of course, equal to this L1 minus L2, right? Bottom, so optical path difference. This is optical path difference 1, optical path 1, optical path 2. L1 minus L2 is my delta L. Okay, L1 minus L2 is my delta L. That equal to 0 for the bright fringe, 0 times lambda. So you can say after insert the glass, okay, L1 to remain unchanged. We only change L1, right? We only change L1 from L1 to L1 prime. So which means after we insert the glass, now my delta L prime become L1 prime minus delta L equal to lambda. Because as I said, L2 remain unchanged, which means after we insert the glass, we make the optical path for the first ray increase by lambda. Right? From this equation minus this equation, I can get my L1 prime minus L1 equal to lambda. So which means after we insert the glass, we make the optical path for the bottom light ray for ray 1 to increase by lambda. So this is from the wave optics. Now from the geometry optics, once we insert a glass, we will, how can we change, for example, the optical path? For example, before we insert it, L1, the physical path is just equal to t plus x. If we assume the sequence here is t, and then the rest of L is x, and then before we insert the glass, as I said, optical path is always equal to n times the physical distance. N times the physical distance. Before we insert this glass, the total physical distance is just the t plus x, right? Because n is equal to 1, so that the optical path is just the t plus x. But after we insert it, the x remain unchanged, but the refracting index of this plate changes from 1 to n, so that the total optical path will now be n times t plus x. So that from geometry optics, the direct definition of the optical path, my L prime minus L should be equal to n minus 1 times t. Okay, this is from geometry optics, direct definition of the optical path. And this optical path should equal to what we get from previous slides, directly from this wave optics, lambda. So that you just equal this t times n minus 1 equal to lambda. You can get, okay, my t is about 500 nanometer divided by 1.56 minus 1. So that you get about 960 nanometer. Okay, so this is the final answer. Okay. So this is the end of our class. Of course, there are some other thin film experiment in the past examination paper, double slit question testing in the final examination. So here I have provided my solutions, to this question. You can take a look. Okay. Now, if you have any questions, so remember we have a consultation session every Friday afternoon. If you have any question, I will still remain here to clear your doubts. Otherwise, the class can be dismissed. Okay. So any question? Any question from student online? Any questions from student online? Okay, thank you, Ziyu. So any question for student in the classroom? Any question? Any question? Any question, guys? Yes, any question? So what's the yes. Yes. Yeah, M can be any integer because of private factors. We can put the private factors. Each so any yes, we just put this. If it's simple, we should do one of this. As I said, then we can use the next between the larger right? You said one of this equal to brighter into this, darker into this. So always this. So all the summary is this. This is the most important thing. All the diffuse formula is best in such a way. You just equal the output plus difference delta L. Clarify either this or this. If the question asks for bright range, understand one of this should be complete. If the question asks for dark range, one of this should be complete. Always this. You can say always I get okay. First, the calculate what is delta L. Let delta L equal to m times alpha or half initial times alpha. All my solution. Yeah, we will go to consider predominant rank. Predominant rank, which means red color is past constructed. Low blue color, which means blue color is reduced constructed. So that you set this delta L for every consider this for blue color, this delta L equals to half integer every plus 1/2 equals this. You can say this is delta L. If I set this to constructed, so this is red products, right? Because red polynomial is value, which means red is enhanced is the constructed. You have to understand this question. The center L equal to m and integer comes the red as equal to another integer plus half the red we plus of the color. And the problem solving.
Then T is the technology.
Yeah, T is the thickness. Normally for something we are looking for the thickness. We want to find out the thickness in order to enhance or reduce a certain time. This is all how the question will be asked. For simple, is always find out the thickness. For double simple, normally find out where the relation of the right range or what the separation of the two simples. So that is normally for the double simple. Okay. Normally for compensation, in order for right or So the object has difference or is related with the geometry or related with the geometry or something. So the distance between the speed and the spring object is the speed and the spring. That is the area. So that we just say the object has no every person or every yes, that's right. Yeah, and then you look at the tutorial question, show me again, the question you can't figure out the problem. Yeah, you if you want to consider online, you need to. But if you on-site, that's all to my office. No problem. Okay. Any question? Other question? Yeah, I would suggest you try to look at it again. So try to look at what I talked about just now in my summary slides. As I said, all the interference problem is set for all people. Calculate the history based on this. But then you look at the action notes underneath the transaction or the I go to the you go to the book and this one should yeah, this is a very good question. This is because if you are never first you have to have ever good circle. You can use circle. Under that circle, so we know if the radius here is a lot much larger than you need a level large circle. But exactly example you ask to draw what I say example only you. No, yes, there are some questions ask you to draw, but a lot of them are wrong. Sometimes actually for what I said, you only use this, but never use three ways.
Although it's not so that I use another one. But
and when you use a third one, you will even in the examination you will get out the not in the second point. But I said only two ways. In practice, what we know is we need whatever good circle, but of course radius. In that case, all the way we reflect from the answer will come to the point. But you know, in the way we can say this is not our good circle. Right? And then you also use in principle 3 or 4 ways. But because of the and you will find the review. So that was the reason. So that is only use the ways. We will only judge, okay? Whether you use a correct record. Do you understand what I mean? Because in the exam, it will also answer calculation. So which means this is what I use more than 2 ways to find the this is because of the one joint of the geometry. So you only have 2 ways. Yes. Yes.
So because it's not good, people have to use 2 ways.
Only 2 ways, yes.
But when you use 2 ways, right, first intersect here. So the image is here. So that's when
the image is where?
you use 2 ways.
Yes, and this is right.
So can you use
Sorry?
because you use 2 ways means the image here.
Yes.
So you said, okay, or
how you physically
in this case, I think how should I put this? So if you ask you to draw, but if you not, if you draw that, the right image space. You should always do the calculation. So if you does not ask you to, you don't draw. Because when you draw, as I said, if you this does not have a very good shape, and the drawing is incorrect. So the question asks you to draw just want to test whether you can know is a digit from vital conversion rate, or you have this hardware rate or you can set a rate, okay? So you just want to test that concept. Okay, if you ask you to draw, no matter this one will be given for one, I believe. But if someone want you to determine the distance, okay, and when you draw it to find out the distance, okay. Okay, any other question? Okay, so take a look again. So, but yes, because I think our quiz is in week 6, week 5. Quiz is in week 5. And then I think it's a time for you to start, I think, week 6. So which means directly after the 4 week 5, we have quiz 1. They don't have to be let me check. But anyway, I think now we already finished on is the time for you to do the reports for the quiz 1.
So you'll be tested on purely geometry.
Yes, not purely geometry. Test until chapter 4. Also geometry and wave optics.
Okay.
Yeah, all geometry and wave optics. So this is why I think week 5 will be a little bit urgent. So too soon. Because we just finished all the quiz. You don't have time to rehearse. Normally we will test it. According to previous scenario, we will have the test in week 6. Because after week 4, you will have another 1 week to do the rehearsal. Then I think they changed in the past for the test in week 6. Sorry?
Week 5, week 10.
Week 7. Week 10 is okay. Week 10 is okay because we only test until chapter and the first 3 tutorials.
Is it the long MCQ or
MCQ.
Computer?
No, only MCQ. So MCQ you make a concept and computer. But it will make you 4 to 6 points. We just choose even computation or calculation is only choose the one of the right solution. Okay, you will get 6 MCQ, I think 6 MCQ. Okay, so the MCQ may be purely concept, or you have to do some calculation and choose the one according to your calculation. Okay, so this is what the quiz will be conducted. You don't have to, for example, the final examination is this. You don't have MCQ, so it's just a question of the calculation until your solution. You know, step by step. That's the final examination. But the quiz is purely MCQ. Only the one right choice. Okay, but that may be concept or calculation. Okay, no problem. Okay, good. Any question?
Good.
Yes. Any question?
I got one question. For this question of question 5, when I consider the 2 rays for these 2, whereby you use this one L prime and L, why do you have a difference of phase which actually cause a wavelength? That which is it that lambda?
This is geometry optics.
Yes.
But this is not geometry optics. This is wave optics. Geometry optics does not have wavelength. Geometry wavelength does not have optics because you put a reflective index and then the optics will only be changed by the reflective index. But for wave optics interference pattern, which means this change of optical path is just equal to lambda. Why? Because in the past, the optical path difference is equal to 0. Now it becomes lambda. Only now it becomes lambda, it can change from 0th order to 1st order.
So that lambda is actually from, for example, from this point to this point.
Yes. From this point to this, because from the shift of the fringe.
Okay.
That is because the shift of the fringe, not caused by the shift of the plates. The shift of the plates causes a change in the optical path.
Okay.
In this way. But the shift of the fringe tell us that optical path is actually equal to lambda.
Okay.
Because this is the only change for lambda, 1 lambda.
Okay. There's one more thing I want to check. Under this one. Where is it? This one. Yeah, this NT. Why do you have the difference between these two? Right? This N is actually, is it a refractive index?
Yeah, refractive of the slab. Times this T. Refractive of this slab. times the t is the optical path of this bit, plus another x is a whole.
So NT is actually the distance, distance or the amount of the
Physical path. T is the amount of the physical path. Is the thickness.
thickness.
Yes. N times the thickness is the optical path.
Okay.
Yeah, in the path then is equal to 1, so that the optical path is directly equal to 1.
Okay, thank you, Prof.
Yeah, no problem. Yes, next week's tutorial as usual. Okay. So no question, I will end the session now. Sorry?
No question.
So I will end the session. Okay, good.
Lam here. All right, so I will be talking about to actually learn LabVIEW on your own. You can